Hello guys, welcome to the lecture 3 of statistical analysis in psychology. This lecture's topic is standard scores and the normal distribution. Let's start with the questions for today's lecture. The two questions. The first one is, how can we interpret an individual value of a quantitative variable in a data set? The quantitative variable, you remember the scale variable in a numeric value. So we can compare an individual value to measures of central tendency of the whole data set. The central tendency and the dispersion, measures of dispersion, those things are descriptions of the whole data set. But today's focus is on the interpretation of an individual value in a data set, in a variable. So, for example, we can compare an individual value in relative to the mean or the median, the central tendency. Or we can consider variability when we interpret a single value interpretation. How does it compares to the standard deviation? And combined together, together with the central tendency and the variability, we can use the standard score, the G-score. It isn't the relative measures, and we will talk about the G-score in more detail today. Alternatively, we can examine individual values' position within the distribution, within the whole data set, in terms of the rank order. What is the rank order of the value in an individual value in the whole data set, in terms of the proportion or in terms of the percentage. These two are different information in terms of the relative locations of the individual value, but it is related to each other pretty tightly in a specific situation. That is the when we have a normal distribution. If we have a normal distribution, the individual value in the normal distribution can be interpreted as the standard score and the percentile rank simultaneously. They are pretty tightly related to each other. The percentile rank interpretation is a proportion or probability interpretation of a specific location. And the standard score interpretation is on the interpretation of the relative location in terms of the mean and the standard deviation. But again, in the normal distribution, these two interpretations are strongly related to each other. Like the functional relations, there are functional relations. And so today's topics, we have 4 topics. Like the first one is we're going to talk about the standard score and the normal distribution and the non-normal distribution and the QQ plot for the normal distribution. So we will discuss each topic one by one. Okay, let's start the discussion of the previous lecture. We talked about the distribution plots for a quantitative variable in the previous lecture. So we looked at the histogram and the density plot and the stem and leaf plot and the dot plot. You remember that? And we also have box plots and violin plot. All these plots are kinds of the distribution plots that reveals the visualize the characteristics of the distribution for the quantitative variable. And we also have the descriptive statistics on distribution, like the distributional characteristics they're expressed by a certain number. For example, the key component is on the center and the spread. So, for example, the mean and the standard deviation is an example pair of the center location and the spread measure. And median and the interquartile range is another pair of the center and spread statistics. There are also some kinds of the shape information, the description in terms of the symmetry versus non-symmetry, and the tailedness. And to represent the non-symmetry, we have a skewness, and for tailedness, we have kurtosis. Those are numbers to represent describe the shape characteristics of the distribution. And we also looked at the quantile locations using quartiles, the first, second, and third quartiles, and the percentiles in terms of the percentage location. And all these, the description is for the whole data set, but not the individual values. But today's focus is on the interpretation of the individual value. Let's start with an example data. So today's example data is directed leading activities. In the data, we have 4 variables. The first one is an identification number of the kids in the school. And the second variable is the group variable, experimental group indicator, one for treatment group and the other for control group. And the third variable isn't just a recorded value, the 0 and the 1 for the 2 groups. And the final one, that is the main variable of today's lecture, the DLP, the performance on degrees of reading power test. DLP represents the degrees of reading power. So it is basically the test scores from 0 to 100. It represents the level of reading comprehension in percent. So let's look at the descriptive statistics for this variable. See here, look at these numbers. So we have the 44 valid observations. The median is 47. The mean is 46 point something. Remember this value. And the standard deviation is 15 something, and the IQR is 16 something. Skewness, we have skewness pretty small number, near 0 skewness, and the kurtosis, it is small also. And the minimum value and the maximum value, the lowest test score was 10, the maximum was 85. And the first and second and third quartile, or the 25th, 50th, 75th percentile were the 40, 47, and 56 something respectively. So we have some sense of the distributional characteristics based on this descriptive statistics of the distribution. But we can visualize the characteristics using the plots mentioned before. So, for example, this is an histogram overlaid by the density plot, density curve. So we see there are a lot of data point like in the center, right? And we can also use the box plot with the violin plot, just like this. And we can clearly see the 2 outliers outside the box area. So basically, it is a kind of symmetrical distribution, but have some like the outliers, a small number of outliers. So we have some like the tailedness in this distribution. Okay, so that's the reason why we have like the positive number of kurtosis and the negative number of the skewness. Okay, but pretty small, right, in size. Okay, let's go to the stem and leaf table or the plot. We see the stems and leaves. Each leaf has represent each observation. And the first one, 1 0, that means like the 1 0, like where is the decimal place? Decimal point is 1 digit to the right of the vertical bar. That means the 10 means the 10, right? Because the decimal point is placed in the one digit to the right of the vertical bar. And so we have a single number of the 10, score 10, and on 17 and 19. And for the third row, we see we have two 33 points and two 37 points, something like that, right? This is the this is the way we read this table or the plot. And we can also see the kinds of the distributional characteristics using the dot plot. We clearly see the 44 dots here, and we see the kinds of the symmetrical, slightly like the tail in the left side, something like that, right? So far, we looked at the characteristics, like the distributional descriptions of the variable degrees of reading power. So let's talk about the standard score right now. Before we talk about the standard score, let's talk about the deviation score first. Because the standard score is a type of the deviation score, the standardized deviation score, actually. The deviation score is the difference between an individual value and the mean of the variable. So operationally, it is simple, like when x is an individual value and the mu is the mean of the distribution, x minus mu is the deviation score. So this deviation score represents how far the individual score deviates from the mean. So a positive deviation score indicates the value is above the mean because like the x is greater than the mean. That will give us the positive number. A negative value deviation score indicates the value is below the mean because the smaller number of x than the mu will give us the negative value, right? If we have a deviation score of 0, that means the value is equal to the mean. The value x is equal to the mean. Now, let's talk about the standard score. Standard score is a deviation score in the unit of standard deviation. That means we divide the deviation score by the standard deviation. It also known as a g-score. The standard score and the g-score is the same thing. So the g-score is the deviation score divided by the standard deviation. It will give us the standard score. Okay? Here, the sigma is the standard deviation of the variable. So how can you interpret the standard score? Just like the deviation score, a positive g-score indicates the data point is above the mean, and the negative g-score indicates it is below the mean. And a g-score of 0 means the data point equals the mean. Up to this point, the interpretation is same as the deviation score. From now on, the specific number of the standard score indicates how many standard deviations a data point is from the mean. For example, the standard score of 1 indicates the data point is 1 standard deviation deviates from the mean. Like it is above the mean by 1 standard deviation. If we have a negative 1.5 standard score, that means that value is 1.5 standard deviation below the mean. Right? So simply speaking, the standard score is the deviation score in the standard deviation unit. Okay? And actually, the most important usage of the standard score is when we have a normal distribution. This is not always true. But if we have a normal distribution, the standard score can be translated in terms of the proportion or probability, because it indicates the percentile rank or quantile rank, and that has some meaning of the proportional location or probability location. Those things we will see, okay? But this is only valid when we have a normal distribution, but not in other cases, okay? Okay, let's talk about the other types of the standardized score, not just for G. Actually, G score has a mean of 0 and the standard deviation of 1 because of the operations. The mean of the deviation score, all kinds of deviation score, like including the standard score, is 0 because we subtract the mean from the original values. And the standard deviation of the deviation score is the same as the original values, but for the standard score G, we have standard deviation of 1. Just like this, that means that we can change the mean and the standard deviation from the original variable, right? But we can still change the mean and the standard deviation of a variable with any number. So any value of the mean and any value of the standard deviation using the following linear transformation. This one, the x nu is equal to G times G here, the standard score, times sigma nu plus mu nu, where the x nu is the new variable with the desired mean and the standard deviation, and the G is the original standardized score, like the standard score, the mean of 0 and the standard deviation of 1. The sigma nu is the desired new standard deviation. The mu nu is the desired new mean. And so we can set any value of sigma and the mu for the new variable. So the common example is a t-score. T-score is widely used and as a standardized score. And in the t-score, the mean of the t-score is usually set as 50, and the standard deviation of the t-score is set as 10. And the other types of the standardized score is an SAT score, but this is an old scale. And in the past, the SAT score, the mean of the SAT score was set 500, and the standard deviation 100. And another very good example is IQ score. Often the IQ score has the mean of 100 and the standard deviation of 15. And we can create these types of standardized variable with any specific number of the mean and the standard deviation by using this operation. Okay. So for example, if we want to create the t-scores from any variable, first we need to create the g-scores. We can do that, right? By creating the deviation score divided by the standard deviation. And then the g-score of a specific variable can be multiplied by 10 plus 50, and that will give us the t-score of the original variable. Okay, but by these types of the standardized score creation, this transformation maintains the relative positions of all scores while shifting the scale. That means this linear transformation does not change the shape of the distribution and the relative positions of scores. It just changes the center location and the scale of the dispersion. Okay, so we call these types of the transformation, it's a shifted and scaled. Okay, let's look at an example data. So our example data, the DLP, the reading power score, look at this, we have the 44 valid observations. You remember the mean was 46 something and standard deviation 15 something. The minimum and maximum values are like the 10 and 85 respectively. Remember that. And for deviation score of the DLP, the means are subtracted for the individual values, right? And then by doing this, the mean of the deviation score is going to be 0. This expression isn't essentially 0, like this isn't like the 0.0000, the 14 number of zeros and something. So this number type, the times that, like the small number, will give us essentially 0. So this isn't essentially 0. But the deviation score of the standard deviation of the deviation score still the same as the original, right? And for the G-score, we have the mean of 0 and the standard deviation of 1, because we divide by all the individual values by 15 point something, and then that will give us the standard deviation of 1. And for T score, after we create this value, we have the mean of the 50 and the standard deviation of 10. We will see in the classroom lectures how this works. But remember, like the second one is on the deviation score from the first variable. The third one is on the standard score of the first variable, and the last one is on T-score for the first variable. All these variables are same in terms of the relative information. Even though we have a different value for the mean and the standard deviation for each variable, we will have the same relative positions and the shape of the distribution. So that's the reason why we have the same shape of the box plot and the violin plot for the first one and the second one, as well as the third one and the fourth one, right? So this is the original variable, this is the deviation score, this is the G-score. No, here, the G-score is here, and the T-score. All these, like the distributional shape are the same, okay? Let's talk about the second topic, the normal distribution. The normal distribution is sometimes called the Gaussian distribution. Is a probability distribution that is fundamental in statistics and many natural phenomena. And it is important in statistics and mathematics. And the normal distribution is also important in investigating the social science or the natural science. The normal distribution is a continuous probability distribution characterized by a bell shape. We see, look at this shape, like it's shaped like bell, right? And the normal distribution is defined by two parameters, mean and the standard deviation. And that's it. If we know the mean and the standard deviation of a specific normal distribution, we understand the whole thing about the distribution. So here are examples of the 4 different the normal distributions with the different value of the mean or the standard deviation. So these 3 have the same mean value, but the different dispersion measures, right? And then this one, the green one, has shifted from 0 to the -2 for the center location, and it has 0.5 for the variance. So all these things, the distributions are normal distribution, the variation of the normal distribution. And actually the normal distribution is symmetrical around the mean, and because of that, the mean, median, and the mode are all equal at the center. And their skewness, the symmetric property is 0, right? So they are perfectly balanced and symmetrical, and that means that they have a zero skewness. Like the mathematical definition of the skewness is an like expected value of the cubic number of the standard score. This is the standard score, right? Standard scores are multiplied 3 times. If we have an extreme value in one direction, it will give us the big number for that direction. That's the reason why we have a negative skew when we have a smaller number, like the big number of the standard score in the left side. That will give us the negative value. If we have a pretty the long tail in the right direction, it will give us the positive number because it will exaggerate it by three times. And like in terms of the kurtosis, normal distribution has the zero excess kurtosis. And actually the calculation of the kurtosis is an expected value of the force power of the standard score, and it will exaggerate the extreme values a lot, right? So because of this, if we have on the long tail, it will give us a big number. And actually the expected value of the force power of the standard score for the normal distribution is 3. So like the excess kurtosis is this kurtosis minus 3. So it will give us the zero excess kurtosis for the normal distribution. Okay? So these are examples of the different distributions with the different level of the tailedness. Okay? And actually in the black curve, this is for the normal distribution, and the excess kurtosis for the normal distribution is 0. And the curve above the normal distribution, the green one and yellow one, the red one, it has a pretty long tail, right? Relative to the black one, the normal distribution. So it will give us a big number, the positive number. And in contrast, and for the distribution below the normal distribution, like for the sky blue one, the blue one, and the purple one here, they have a pretty short tail or no tail at all, right? So, and those things, they have the excess kurtosis of negative number of the excess kurtosis. And for example, this one, the rectangular type of the distribution called the uniform distribution, it will give us the minus 1.2 excess kurtosis. That represent the pretty short-tailed distribution. Okay, let's talk about the characteristics of the normal distribution in more detail in terms of the proportion of the area. This is the kinds of the typical type of the normal distribution, and we see in the x-axis the normal distribution of the mean of 0. In this case, it doesn't necessarily be the case, but for this example has the mean of 0. And from the below and the above the 1 standard deviation, it is colored by blue, right? And this is like the center of the distribution, and it covers a lot of areas, like 68% within the 1 standard deviation. So about 68% of the data falls within 1 standard deviation of the mean. That is fixed. This amount, this ratio, this proportion is fixed for the normal distribution, any normal distribution. and about 95% within 2 standard deviations of the normal distribution, okay, of the mean, like from here to there. So from -2 standard deviation to the +2 standard deviation, the area of this interval covers 95% of the total area. That is the fixed characteristics of the normal distribution for any normal distribution, for with any mean, any value of mean, and any value of the standard deviation. Same thing. And about within the 3 standard deviation, like from the -3 standard deviation to the +3 standard deviation, it covers almost the whole area, but not perfectly. So actually the 99.7% of the total area has covered within the interval, this area. And this number is exactly the same for all kinds of the normal distribution with different means and different standard deviation, all the same. So this is the main, the important characteristics of the normal distribution. So you remember that in terms of the standard score of the normal distribution can be translated in terms of the probability or the proportion of the relative location. Okay. So you remember that normal, because of these characteristics, and the normal distribution is pretty important. Why? You remember that many natural phenomena approximately follow a normal distribution. This is one like the scientific reason, and the other, like the more theoretical or mathematical reason, is on central limit theorem. We will cover this topic later. And the means of large samples tend to be normally distributed. This is a pretty important the characteristics of the normal distribution. So we will come back this topic later. And the normal distribution is the basis for many statistical methods and inferential statistics. Because inferential statistics involves the calculation of the probability, and one of the easiest like the way to calculate the probability is using the normal distribution in statistics. And there are many applications in science and the mathematics or statistics. Like for example, in social sciences, the IQ scores are typically assumed to be distributed as normal, and like the height of the people, the individuals, the height distribution is approximately the normal distribution, something like that. In natural sciences, the measurement errors follows the normal distribution, presumably, and there are many like the physical phenomena that just follows like the normal distribution, like kind of the characteristics. And in finance, for example, the stock price changes or risk modeling, we can use a normal distribution a lot in this area. So there are many applications using the normal distribution. And there is one specific normal distribution and widely applicable to the many settings. The standard normal distribution. So we have the different value of mean and the standard deviation for any normal distribution. But if we have a mean of 0 and the standard deviation of 1 for the normal distribution, this is the normal distribution, the standard normal distribution. So this is a specific case or special case where mean is equal to 0 and the standard deviation equal to 1. And like because of these characteristics, we can express the values in the standard normal distribution using g-scores, right? Like in the unit of the standard deviation. So g-scores in the standard normal distribution can be easily interpreted as probability. You remember that in the normal distribution, we can calculate the probability or the area under the curve with a specific interval in terms of the probability, right? So, for example, from minus 1.96 to the positive 1.96 of the g-score, the probability of this interval is always 0.95. It is fixed number. So we use this interval a lot for the 95% confidence or the 0.95 probability of the total area. On these characteristics of the standard normal distribution, we can interpret an individual value assuming the normal distribution. The standard interpretation of a single value assuming a normal distribution typically involves converting a value to a g-score, the standard score, and then interpreting its position relative to the mean. For example, first we can calculate the g-score using this operation, and then interpret the g-scores in terms of the probability, just like what we have done before. Like g-score of 0 is the value is exactly at the mean, and g-score of plus minus 1 is about 68% of the values fall within this range, plus minus 1 standard deviation, or the g-score. Or g-score of the plus minus 2, about 95% of the values fall within this range. So for the plus minus 3, g-scores about 99.7% of the values fall within this range, right? And like the other common interpretation in terms of the interval or the range, the absolute value of the g-score smaller than 1, that value is within 1 standard deviation of the mean. And we can consider those scores within this range is considered typical values. You remember that 68% of the values are around the center, typically. And the absolute value of the g-score greater than 1 and the smaller than 2, the individual values within this range is somewhat unusual, like outside the center typical range. So we interpret these values as unusual, somewhat unusual. But that's not a pretty extreme case, right? Unusual but not extreme. In the values, the absolute value of the g-score, the greater than 2 and less than 3, these values are quite unusual, right? So outside the 2 standard deviation, like the less than 5% observations are there. So these are very unique and abnormal kinds of outliers, right? Quite unusual. And actually, if the values, the g-scores, the absolute value of g-score is greater than 3, it is pretty rare or pretty extreme. You remember that within the 3 standard deviation plus minus, there are 99.7% values. So outside the range, like smaller than 0.3% are there. So it is pretty rare case or the extreme case. In terms of the percentile, the g equal to 0 corresponds to the 50th percentile. G-score of 1 is approximately the 84th percentile. G-score of -1 is approximately the 16th percentile. G-score of 2 is approximately 97.7th percentile. and z-score of -2 is approximately the 2.3rd percentile. In the same way, the z-scores can be converted to a probability using a standard normal table or calculator function. So we can have the probability interpretation for the z-scores. And this interpretation assumes the data follows a normal distribution. And for non-normal distributions, like the different interpretations or transformations might be necessary, or we cannot use the same probability interpretation as the normal distribution. And let's look at the probability density function itself. This is a normal distribution with mean of 0 and the standard deviation of 1. So for the interval of -infinity to the positive number 1, we have the cumulative probability of 0.84. And actually, the area of this under this curve is exactly like this one. If we change the interval, we can get the different number in terms of the cumulative probability or the area under the curve. For example, let's look at this one. Here we see we plot here from minus infinity to 1. If we change this number like up to 0 point, it will give us the 50 instead of the 0.84, like 0.5, right? So the area under the curve or the cumulative probability is determined by this interval, the location. Okay, so if we put some number, it will give us a certain probability, cumulative probability, or the area under the curve. Okay, let's type 2 instead of 1, and it will give us the about approximately 98%. In more precisely way, like the 97.7. You remember that, okay? And we can get these kinds of numbers not just using this like the plot, but we can use the function, the normal distribution functions. To get the probability, we can use a p norm up to this point. For example, like here, the up to 0. What is the cumulative probability of the standard normal distribution? Is 0.5, right? And what about this? Like the from negative infinity to minus 1.96, what is the probability, the cumulative probability within that interval for the standard normal distribution? It is 0.024 something. It's like the 2.5% approximately. So up to that point, like here, right? This isn't like the 2.5% something. And just because this isn't the symmetric distribution, we have the same amount of the area like the greater than 1.96, right? So that's the reason why we have the total of approximately 5% outside the range, like the smaller than minus 1.96 and greater than 1.96, something like that. So if we calculate the p norm of 1.96 up to this point, and then subtract the remaining part of them up to this point, here, minus 1.96, it will give us about the 0.95. That's the reason why we have the interval, 95% interval with the plus minus 1.96 standard deviation in the normal distribution. So we can look at this from like this one using minus 1.96 to 1.96, and it will give us the value. See here, exactly 0.95, right? Okay. And what about the p norm 2? What will give us, this one give us in terms of the cumulative probability? It's 0.977 something. Okay, so this is a cumulative probability for the standard normal distribution, the mean of 0 and the standard deviation of 1. And what if we have a different value for the mean and the standard deviation? We can still use the same function with the specification of the mean and the standard deviation. So for example, if we have a mean of 100 and standard deviation of 10 for a specific normal distribution, and we want to know the probability, cumulative probability from minus infinity to this point, it will give us the cumulative probability. Because this is a 2 standard deviation above the mean, it the proportion or the cumulative probability is same as the p norm 2 for the standard normal distribution, right? And for this one, the second part is the mean, and the third part, the element is standard deviation. So this means what is the cumulative probability of the normal distribution with the mean of 100 and standard deviation of 10, and up to the 110, just one standard deviation above the mean at that point, right? And that will give us the 0.84 something, right? And then and subtract the probability, cumulative probability for the same normal distribution up to the point of 90, and this will give us the cumulative probability for the interval, specific interval, from -1 standard deviation to the +1 standard deviation. So within the 1 standard deviation, what is the cumulative probability for that interval? And this is the number. So we know that. So actually, we already know the 68 point something % are within that interval, right? What if we want to know the location based on the probability? Just the reverse situation for the previous example. For example, where is the point, the quantile point for the distribution, cumulative probability of 0.5 for the standard normal distribution? That is 0, right? So you know what I'm saying? The probability of normal distribution up to 0 is exactly 0.5, and so that's the reason why we have the location of 0 for the standard normal distribution. That gives us the cumulative distribution, the probability of 0.5 up to that point. And for the probability, cumulative probability of 97.5% or the 0.975, where is the location? So that location is 1.96, just like this one. You remember that? This one. No. Exactly this one. So we lost the number, but it is what it is, right? So up to this point, the both side plus minus this number outside inside this interval, it will give us the 0.95 the interval probability, and outside the interval it will give us the 0.05 probability, right? And for the normal distribution with a mean of 100 and standard deviation of 10, and where is the point, the score, the value for the cumulative probability of 0.975 from negative infinity to that point. That point is approximately about 120 because we have a standard deviation of 10. So 2 standard deviation above the mean will give us approximately that amount of the probability, right? So, and it will give us the like the 1.96 times this number, so 1.96, right? So this is the number. So we can get these numbers easily by using this function. So and you can use it and you can practice it in the classroom practice. Okay. Okay. So like for the remaining part, let's skip this part and leave it as an activity in the classroom. Now let's talk about a non-normal distribution, and in this case we will use an chi-squared distribution. This is a typical non-normal distribution, and we will use a lot in the later lectures. We will use a chi-squared distribution a lot. So let me introduce a pretty quick introduction, the brief introduction of the chi-squared distribution. And this is an example of the chi-squared distribution, and this is a chi-squared distribution with df equal 5. df represent the degrees of freedom, and it is just like the mean and the standard deviation for the normal distribution. The degrees of freedom determines the location and the scale and the shape of the chi-square distribution, and it has just a single parameter for the distribution, characteristics of the distribution. This single number determines everything about the distribution, the chi-square distribution. Okay, and the characteristics. The chi-square distribution is the chi-squared distribution is a continuous probability distribution, just as the normal distribution, and of the sum of squares of k independent standard normal random variables. And let's skip this part. It's just a mathematical definition of the chi-square distribution. I will explain this in more detail later if we have enough time. When we use this specific distribution later. And the key properties of the chi-square distribution is it has always a positive number, non-negative number. So it's a right skewed. So sometimes it has sometimes zero value, but there's no negative values in the chi-square distribution. Because of this one, the distribution always have the right skewed shape. And chi-square distribution has one parameter, the degrees of freedom. And the degrees of freedom, if degrees of freedom increases, it approaches a normal distribution. At this point, this is the chi-square distribution with degrees of freedom of 5, and it doesn't look like a normal distribution. It is not non-symmetric, and it has the tails in the right direction. So, but if we have like a very big number of degrees of freedom, it looks like the normal distribution. Let's look at that part. And for this one, here we have like the degrees of 5. What if we use 15 instead of 5, and then use 30 like this one? It looks like more like the normal, right? It approaches shape of the normal distribution. What if we use 30 instead of the 15? and then use on 60 for the limit, the range, and this is the shape of the chi-square distribution with degrees of freedom of 30. So it approaches the shape of the normal distribution, right? Let's go back to the original degrees of freedom and the scale. And now let's go to the description of the characteristics. The shape of the chi-square distribution is asymmetrical. That means non-symmetric, and light skewed for low df, degrees of freedom. So, and like the almost symmetrical for high value of the degrees of freedom, right? And it becomes more symmetrical as the degrees of freedom increases. And what is the applications of this distribution? We will use this distribution later in the lectures, like the later classes for the semester. And it one application is Gunis of fit test for the there are many situations this applies. And another one is an independent test in contingency tables. We will talk about this when we deal with the associations between the categorical variables. And and at that time, we will use the chi-square distribution for the test of the independence. And it also is used for estimating the variance in normally distributed data. So you remember that basically chi-square distribution consists of the sum of the squared values of the standard normal distribution. So it is highly related with the normal distribution. And let's look at the comparison to the normal distribution. In terms of the shape, normal distribution is symmetrically bell-shaped, bell-curved, but the chi-square distribution is light-skewed, and especially for the low degrees of freedom, you know that already. And the range of the normal distribution is -infinity to +infinity. But the chi-squared has the limit of the 0, so it always have the non-zero values. So the range is 0 to +infinity. The parameters of the distribution for normal is mean and the standard deviation, and they determine the characteristics of the normal distribution. But for chi-square distribution, it is defined by the degrees of freedom, so single parameter distribution. Okay, and the central tendency in case of the normal distribution, the mean, median, and mode are the same because they are perfectly symmetrical. But for chi-square distribution, the mean is greater than the median, and the median is greater than the mode. Always, because it is the right-tailed distribution. And the relationship between the two, the chi-squared distribution is derived from the normal distribution, as I explained before, right? And as degrees of freedom increases, the chi-squared distribution approximates a normal distribution. This is a pretty interesting characteristics, but we will not use this kind of things at this point. And in terms of the standardization, in the normal distribution, we use z-scores a lot, and the standard scores are pretty widely used in the normal distribution. But for chi-square distribution, no, we don't use z-scores at all in the chi-square distribution. It doesn't have any information in terms of the probability. So the point here is for non-normal distribution, we cannot use the z-score in terms of the probability interpretation. in a later lectures, we will talk about the hypothesis testing about the many statistical analysis. And for the normal distribution, we will use this distribution, the normal distribution, for hypothesis testings about the means and the proportions with large samples. And for chi-square distribution, we use that distribution for testing hypotheses about the variances and the categorical data analysis. So we will see. In summary, while both of the continuous probability distributions, the two distributions are both the continuous probability distributions. They have distinct shapes, ranges, and applications. And the chi-square distribution is derived from the normal distribution, but has unique properties that make it suitable for specific statistical analysis, as explained before, particularly those involving variances and categorical data. So we will see this part later. Okay, let's talk about the fourth topic of today's lecture, the normal QQ plot. Here we have three variables and the descriptive statistics for the three variables. The first variable is the reading power, the original variable. The second one and third one is a random samples from the normal distribution and the chi-square distribution. So I created the random samples from the normal and the chi-square distribution, 44 observations each. And look at here, like the mean of the second variable is approximately 0 because I used the standard normal distribution for this part, and the standard deviation is pretty similar to 1, and the skewness is near 0, and the kurtosis is like the small, although because this is a random sample, it is not exactly 0, but it is pretty similar to 0. And for chi-square distribution, the skewness is 1.6. It's big number, so right skewed number. And for the kurtosis, like the 3.1 is pretty long tail distribution. So look at these three distributions of the three variables, like this one. The first one is the original variable, the reading power. We are familiar with this shape. And the second one is from the normal distribution, and the third one is from the chi-square distribution. So we clearly see the skewness and kurtosis for the third distribution, but not for the normal distribution. But it is pretty, look at this, the histograms and the density plot. It is difficult to decide each distribution follows the normal distribution or not. You can compare the first one and the second one, which one is more like the normal distribution. By looking at the histogram, it is difficult to determine which one is more similar to the normal distribution. And clearly, if this is the case, we can say that the shape is not normally distributed. But in case of these two, it is difficult to differentiate and then which one is the closer to the normal distribution, right? And in terms of the number, that the skewness and kurtosis, still we have some vagueness in here and there. So to determine a specific distribution follows the normal distribution or not, we use a QQ plot. QQ plot. And like this one, QQ plot is we can use for the normal distribution and for the other distribution, but the QQ plot for normal distribution is widely used. And here, this is on the QQ plot. So the x-axis is on theoretically normal quantities, and the y-axis is on just on sample statistics, the sample values. So this is a scatter plot between the two. If we have like the linear type of the scatter plot, we can say that the distribution, in this case like the all normal distribution, is pretty same as the normal distribution in terms of the shape, but not for the DLP or the R square, R chi-square. Okay, so let's summarize the QQ plot. For the QQ represent the quantile, and it is a graphical tool used to assess whether a data set follows a particular theoretical distribution, and most commonly the normal distribution. So we can use on QQ plot for other distribution, but most of the cases we use on QQ plot for the normal distribution. When used for test for normality of the distribution, it's often called a normal QQ plot. What is the purpose of the QQ plot, the normal QQ plot? To visually compare the distribution of a sample to a theoretical distribution, usually normal, and to identify deviations from the assumed distribution. So how it works? Plots the quantiles of the sample data against the theoretical quantiles of the normal distribution. And if the data is normally distributed, the points in the scatter plot will approximately lie on a straight line. So this is a strong evidence of the similarity between the two distributions in terms of the shape. And here there is some the steps to construct the QQ plot, but I want to skip this part. Just forget about this part. And what is the interpretation of the QQ plot? A straight line is a data closely follows a normal distribution. If the scatter plot is an S-shaped curve, the interpretation of this curve is data has lighter, shorter tails than a normal distribution, or heavier tails for inverted S-shaped. And for the curve of the line is a light skewed data, and I will show you an example. And curve below the line, the left skewed data. And if there is outliers, it appears as points far from the line at the ends of the sample quantiles with inverted S-shaped tails. So the advantage of the QQ plot is a visual and intuitive investigation of the normal distribution, and can detect various types of departures from normality. And it works well even for small sample size. But the limitation is interpretation can be subjective, and it doesn't provide a quantitative measure of normality. Because of their limitations, we can use a complementary test for the normality inspection, and often used in conjunction with the numerical tests like Shapiro-Wilk or Anderson-Darling test for a more comprehensive assessment of normality. Simply speaking, if your data is normally distributed, when you line up its quantiles against the quantiles of the theoretical normal distribution, they should match closely, forming a straight line on the QQ plot. So using the strategies below, we can say that when we have scatter plots on the straight line in the QQ plot, we can say that the variables are distributed pretty normal. And in case of we have like the curve above the line, we can say that this distribution has positive skew. And if we have a curve under the line like this one, we can say that that is a negative skew distribution. And for this one, if we have an S-shaped, not this one, S-shaped is like the lower level of kurtosis, but in case of this one, like the inverted direction of the the letter, we can say that this is a pretty heavy-tailed distribution. Okay, that's it. And I will explain in more detail in the classroom for the remaining part.